And the correct answers here, in my opinion, are the first two. The first one is, even if the algorithm makes an error with 90% probability, running it only a few times does guarantee a correct solution. And that is, of course, as you've seen before, these probabilities here have to be multiplied with each other if we run the algorithm a couple of times. So if we run it the first time, of course we have a 90% error chance. But if we run it a second time, we only have 90% squared error chance. If we run it 3 times, we have 90% to the power of 3. And once we have run this algorithm 50 times, we have an error probability of 90% to the power of 50, which is about 0.5%. And running it a couple of times more, of course, we can even get this figure much, much lower. So since we only have to run it a constant number of times to get the error very, very low, it would mean that we're staying still in polynomial time, but we're almost guaranteed a perfect solution. Now, I'm not saying that this is impossible, because the laws of NP completeness indeed do not account for randomness, but of course it's very, very unlikely. It's almost the same as with the approximation algorithms, where you wouldn't expect an approximation algorithm with an approximation factor of 1.01, even though for some problems it has not been proven that that is impossible, but you still wouldn't expect it. Now, the second choice here I think is also correct, and that is basically my reasoning why I say you shouldn't expect this. The number of potential solutions for an NP-complete problem is exponential. Since the algorithm only runs in polynomial time, it can only afford to check a small part of that solution. That is basically the image that we just had, where you're only able to explore small areas of the whole solution space. And of course, you have to employ the strategy. I just think that with this strategy, it's highly unlikely to get an algorithm with this performance up here. It just doesn't make sense because you're still poking around a lot. So why would you get a fixed error probability in an exponentially large space if you can only afford to check a polynomial-sized part of it? And finally, as I said, the laws of NP completeness indeed do not account for randomness, but the thing is this: just because that is so, doesn't mean we should expect anything to happen. Again, I think this is the same thing as with the approximation algorithms. Of course, for some problems, it would theoretically be possible to have a 1.01 approximation algorithm, but it just seems too unlikely to be true.